You hear about climate change all the time in the headlines. But today, we're going to get under the hood. We're going to look at the actual gears that drive our planet's climate machine, the raw physics of the system itself.
So, just for a second, I want you to imagine you're standing inside a giant clock. I mean, this thing is the size of a planet, and its gears, they're not brass or steel, no. They're made of air and water and ice. You've got this massive gear of ocean water grinding against the gear of atmosphere, which in turn is torquing this unbelievably slow-moving gear of ice at the poles. It's a beautiful and kind of terrifying interconnected machine.
So here's how we're going to break this thing down. We're going to look at it gear by gear. First, we'll start small, with the air right above a city. Then we'll scale way up to the ocean, and then the planet's ice shield. From there, we'll zoom out to geological time to really get the machine's natural rhythms. And then we'll look at the new gear humans have added and what happens when these two different speeds collide.
Okay, let's start with the gear that's easiest to relate to. The air that we all breathe every single day in our own cities. Come on, you've had those days, right? You walk outside and the air just feels heavy. It's thick, it's hazy. Well, turns out there's a very specific physical mechanism that causes that feeling.
It's called a temperature inversion, and it basically flips what you think you know about the atmosphere completely upside down. See, normally, air gets colder the higher up you go. But during an inversion, a layer of warm air just slides in over the top of the cooler, denser air that's sitting near the ground. And just like that, it creates a trap.
So what does this actually do to the air quality? Well, on a normal day, the warm air near the ground rises, right? It's like a natural ventilation system, carrying all the pollution up and away. But an inversion completely breaks that system. That warm air layer acts like a lid on a pot, and all the cool, polluted air underneath, it's trapped. It has absolutely nowhere to go.
And when the air gets stuck, everything in the air gets stuck with it. The pollution just builds and builds and builds hour by hour. And you feel it right away. You get that hazy, smoky air, your eyes start to burn, your nose. The air quality index, or AQI, just skyrockets. For a lot of people, it literally gets harder to breathe. It's a direct physical assault on your body.
Over the long term, it gets even more serious. Places with frequent inversions see spikes in ER visits, especially for kids and the elderly. You see higher rates of asthma and other chronic breathing problems. And it's not just us either. All that trapped pollution stresses out plants, damages their leaves, and can choke out an entire local ecosystem.
All right, so that's the local air gear. Now, let's scale up, like way up, to a gear that's the size of an entire hemisphere, the ocean engine. And we're going to focus on the Pacific and its, let's call them dramatic mood swings, better known as El Niño and La Niña.
To get a handle on these extremes, first you have to understand what normal looks like. Typically, you've got these strong trade winds pushing warm surface water from east to west across the Pacific. This lets cold, nutrient-rich water rise up from the deep off the coast of South America. That process is called upwelling. Now, during El Niño, those winds weaken or even reverse, and all that warm water sloshes back east. And during La Niña, the whole system goes into overdrive. Super strong winds, super strong upwelling.
Which leads to a pretty amazing question, right? How does a change in wind speed out in the middle of nowhere cause a massive flood thousands of miles away in California? Well, the answer is a concept called teleconnections. In a gear this massive, a little tweak in one spot can directly trigger huge weather changes all across the globe.
Just look at the chain reaction from a strong El Niño. That warm water sloshes back to South America, and it completely shuts down that nutrient-rich upwelling. Without those nutrients, the tiny plants in the ocean die, the anchovies starve, and boom, the entire Peruvian fishing industry collapses. At the same time, all that warm water is evaporating, causing insane floods and landslides in the normally bone-dry deserts of South America, while Australia, which usually gets that rain, is hit with severe droughts and bushfires. You've literally swapped the weather between two continents. But don't think for a second that the cool phase, La Niña, is some kind of calm break. Nope, it's just a different brand of extreme. The trade winds get so strong they push a ton of warm water to the west, leading to intense flooding in Australia and Southeast Asia. At the same time, the supercharged upwelling off South America creates a fishing boom. And this is crucial for those of us in North America. La Niña pushes the jet stream way up north, which can lead to severe drought and fire conditions in the U.S. Southwest.
Okay, we've seen the air and the ocean gears. Now let's turn to the planet's great regulator, the cryosphere.
This is all the world's ice, and it acts like a giant reflective shield. It's Earth's natural cooling system.
And to get how ice cools the planet, we just need to understand one simple idea: albedo. And you already know what this is, you just might not know the word. Think about wearing a white t-shirt versus a black t-shirt on a hot sunny day. The white shirt has a high albedo. It reflects the sunlight and keeps you cool. The black shirt has a low albedo. It absorbs the sunlight and you get hot. Well, on a planetary scale, ice is Earth's white t-shirt.
Now, think about the time scales here for a minute. The atmosphere can change its temperature in minutes, the ocean, months, maybe years. But these massive ice sheets, they act as the climate's long-term memory. It takes thousands of years for them to grow or shrink. So when we start seeing them shrink in our lifetimes, that's not a weather event. That is a signal of a fundamental shift in the entire planet's energy balance.
And this is where it gets really dangerous, because losing ice kicks off one of the most powerful positive feedback loops in the entire climate system. And remember, in physics, positive does not mean good, it means it amplifies itself. So let's walk through it. A little bit of initial warming melts some ice. Okay, but that exposes the darker ocean or land underneath. That dark surface has a lower albedo, so it absorbs more sunlight, which increases the temperature, which, you guessed it, melts even more ice. It's a relentless, self-perpetuating cycle.
So, we've seen how the machine works right now. But to really understand what's happening, we have to zoom way out and look at the slow, natural rhythms that have been running this planet for millions of years. Which brings us to a really important question. Hasn't the climate always changed? You hear this all the time. And the answer is yes, absolutely it has. Earth has gone from a snowball to a hothouse with palm trees at the poles and back again. Natural forces have always been at play. The real question isn't if the climate changes. The key is understanding the drivers and, critically, the speed of that change. Just look at the different speeds of those natural gears. You've got Earth's orbital changes, the Milankovitch cycles, which are really powerful, but they operate over tens or hundreds of thousands of years. Then you have things like big volcanic eruptions that cause dramatic but really short-term cooling, and solar cycles happen over decades. As you can see, the timescale is everything. Those Milankovitch cycles are basically the pacemakers of the ice ages. They're these three slow, predictable wobbles now the Earth moves through space: the shape of its orbit, the tilt of its axis, and the wobble of that axis. Over tens of thousands of years, they work together to control how much sunlight reaches different parts of the Earth, slowly pushing us into and out of ice edges.
Okay, so what about the other natural suspects? Well, here's a fun fact. Big volcanic eruptions actually cause temporary cooling. They blast all this stuff into the stratosphere that acts like a giant sunshade, reflecting sunlight back into space. And the sun itself? Well, we've been measuring it with satellites for decades, and its total energy output has not gone up in the last 50 years. In fact, it's been trending slightly down, even while global temperatures have been soaring.
So, if the big, slow orbital cycles are moving way too slowly to explain what's happening now, and the faster natural drivers like volcanoes and the sun are either cooling us or just aren't changing, then that must mean a new gear has been added to the machine. And this right here, this is the fundamental difference. Natural climate change in the deep past was driven by physics, orbital mechanics, geology, stuff unfolding over millennia. Today's change is driven by chemistry, the rapid injection of greenhouse gases into the atmosphere over just a couple of decades.
If you're looking for the smoking gun of climate science, this is it. When scientists run their supercomputer models of the last century's climate using only the natural drivers, the sun, volcanoes, orbital shifts, the models actually predict that we should have had a slight cooling. It is only when they add in the human-caused greenhouse gases that the models perfectly match the warming that we've actually observed.
And this brings us to our final and most important point. We've looked at the slow, powerful, ancient gears of the natural climate machine. And we've identified this new, incredibly fast-moving human driver. So, what happens when these two radically different speeds collide?
Let's go back to that clockwork planet. For millions of years, this machine has been governed by these massive, slow-turning gears, set in motion by the gravitational pull of other planets and the deep rumblings of geology. But in the last century and a half, we have come along and bolted on a completely new gear. One that's driven by chemistry, and it spins with a speed and a force that is totally alien to the original design.
And so we are left with this one massive question.
What happens when you force a brand new, high-speed gear to grind against an ancient, slow-moving machine? Are we just overriding the natural cycles? Or are we creating some kind of chaotic, new friction between geological time and human time? Understanding that we are no longer just passengers, but that we are now the drivers of this